Okay, hello Cloud Gurus! Welcome to this lecture where we're going to take a look at how data makes its way from the front door of Google's network to the correct resource in our system. So let's think about some of the reasons why we might want to direct data flow to different resources. Well, like I just mentioned at the end of last lecture, one of the reasons is latency reduction. You want your system to respond quickly to users, so it's good if your servers are physically close to them. It may seem strange, but even data traveling at the speed of light takes a noticeable amount of time to cross the globe. But another circumstance where we need to direct data flow to different resources is simple load balancing. Let's say you have too many incoming requests to be handled by just one machine, so you add a second machine to help out. But there's no point in doing that if all of the incoming requests still go to the overloaded machine, right? That's why we need load balancing, to divide the requests up amongst the machines that can handle them. Now I'd like to point out that load balancing is separate from autoscaling, and that's why I went out of my way to cover autoscaling to handle fluctuating workloads before we got into this networking stuff. Most other labs you'll find, like code labs or whatever, will cover both of these two together. And I mean, of course they do work well together, but I want you to build a mental model that has them related, not entirely overlapped. Now, one other circumstance where we might need to direct traffic differently is for system design. In particular, you might have different servers in your system handling different parts of that system. And this is especially true when your service is composed of microservices rather than all jammed together in a monolith. So if you imagine something like an online store, you might have some systems that handle the item catalog, maybe other systems that know about the current inventory levels, and yet different systems that handle user data, like past orders that they've placed, or maybe even what's in their cart right now. So if we think about how we might address these circumstances in Google Cloud, latency reduction is something that we can do with cross-region load balancing using global Anycast IPs. If you use premium tier routing and have a global Anycast IP address that points to Google's network, Google can then decide where to send that inside of Google's network right at the point of presence, the edge location where the data comes into Google's network. Now, for the more normal load balancing, where request volume just goes up and down, Cloud Load Balancer is the umbrella term for lots of different types, including internal and external load balancers, and also load balancers at both Layer 4 or Layer 7, which I'll talk a little bit more about in a bit. Now, to handle the microservices type circumstances, this will often use the HTTP or HTTPS load balancer with an URL map so that different paths can go to different places. This also we'll take a closer look at in just a minute. Now you can read more about all of the different ways of load balancing at this link, and if you decide to dig further into just one of those load balancing types, I think it should be the global HTTPS load balancer. That's the most powerful one and the most likely to show up on your exam. Now, I've used these terms a couple of times already, but it's valuable for you to have a better understanding of what unicast and anycast are. These are routing schemes, and they describe how data can get from one place to another. Unicast says there is only one unique device in the world that can handle this, so send it there. Whereas Anycast says there are multiple devices that could handle this, send it to any one of them, but ideally the closest one. Almost all IP addresses that you've seen before will have been unicast, so it's quite special that Google offers Anycast IP addresses that we can use. Anyway, another thing to clarify is this whole Layer 4 versus Layer 7 thing. Now TCP of TCP IP, which is the primary protocol we use to send data around the internet, is usually considered to be at Layer 4 in the OSI model that I mentioned earlier. Now at this level, there are really only IP addresses. It knows how to make a connection from one place to another and send a lot of data along that connection, but it doesn't know anything about things like HTTP or HTTPS. Those protocols that make up the web work at Layer 7, and this is where URLs and paths come in. So if you have something like mywebstore.com/shopping cart, the /shopping cart part is the path. Now, because the top layers, like HTTP, are built on the lower layers, like TCP, this means that for something to be able to route based on the path, it needs to understand layer 7. If you're routing based on layer 4 information, you simply can't handle the path. So let's say that you have a bunch of packages and you put all of the delivery addresses inside of the packages, and then you lock them up tight in the back of a freight truck. If you now tell the driver to take all of those packages to the right place, based on the addresses that are inside of the packages, it's pretty obvious that the driver won't be able to know where they go. They can't see the delivery addresses. Now that might be a bit of a weird analogy, but it might help you remember why you can't route based on the path at layer 4. Maybe you've heard about how other clouds or systems can do global load balancing with DNS. Well, the name resolution that happens through this domain name system can be the first step in routing. It is possible to say that when you're looking up mywebstore.com and turning it into an IP address, that is the point in time when you decide where to send that client. Do you send them to the copy of the website in California, or London, or wherever? Well, this can work, but to be honest, it's kind of a crummy system. It has a number of problems. The first problem is that the DNS lookup really only returns you a layer 4 IP address. It doesn't know what the full path is, and it can't make any decisions based on it. This makes your global load balancing an all-or-nothing proposition, so every part of the system has to be replicated in every region. But another problem is that DNS lookups are very chunky. Oftentimes you'll find that one single DNS query is cached and reused for huge sets of clients. This can often happen with ISPs or large corporations, and it can mean that even though you want to send half of the traffic to one resource and the other half to another resource, you could wind up getting almost all of the traffic to one of them and almost none of it to the other. Obviously, that's not what you want from a load balancing perspective. Now, a related but still different problem is that DNS lookups tend to be sticky. What this means is that they lock on to a particular target. Now, this is actually by design in that every DNS lookup comes back with a TTL, a time to live, saying how long that particular DNS lookup is valid. So if you return a high TTL, saying that the lookup is valid for a long time, then clients can continue connecting to either overloaded or maybe even completely dead machines. They'll never stop trying to connect to that machine until the TTL expires and they do another lookup. So I guess the response then is to say that the lookups don't last very long. But if you return a 0 or very low TTL for every request, it means that every single connection has to redo the DNS lookup too, and that comes with significant cost. It means that each time a client connects to your system is going to be slower, because it needs to do both the DNS lookup and the connection to the system. But there's also a money cost to consider because all of that extra DNS request processing will cost something too. And that really leads into the next problem anyway, which is that DNS lookups rely on the client always doing the right thing. And here's a spoiler, they don't. There have been many documented cases of clients doing absolutely the wrong thing with the DNS TTLs. Even if the TTL is set very high, maybe they'll look it up every 5 minutes. But that's actually really not that big of a problem because at least you get the opportunity to respond with the current information. The real problem is that if you set the TTL to 0 and they wait 5 minutes, that's 5 minutes of that client doing absolutely the wrong thing. Maybe trying to connect to a machine that's gone away. In the end, it doesn't really matter if it's your fault or the fault of whoever made that client's device. If that person can't use your system for an extended period of time, it's your problem. And ideally, you would design your system to avoid that kind of problem. So that's really why I so love the premium tier cold potato routing with these global Anycast IPs. So the last thing we want to look at in the context of routing is getting data from one resource to another. And for that, I'll see you in the next lecture.